So then it begs one really strong question, right? And I think it's probably one of the most important questions in this whole chapter. Question. Why do heavier nuclei require more neutrons? And to really answer this question, we need to understand the role of the neutron in the nucleus. That's what we got to do. So here we go. The role of the neutron. The role of the neutron. So in order to understand what the neutron does, we have to recognize two things. There are two competing forces within the nucleus, right? We have F strong, and we know that's an attractive force, versus F electrical, which we know that that's a repulsive force. These guys are always competing with each other. The neutron role is to act as a glue. So it acts like a glue, and sometimes you'll hear it called neutron glue, that helps to hold the nucleus together. So it's the glue that does that. And so what we find here is that I'm going to pick 3 atoms again. Okay, so I'm going to start with light, and then I'm going to go to midweight. So the first one, so if I start with the light nuclei, what do we see with the light nuclei? Well, with light nuclei, I could pick a different atom that's less than 20. And the simplest one is, without any doubt, helium. So if you look at helium, what's special about helium? Well, we know that helium looks like this. So it has 2 neutrons and 2 protons. And so what you're seeing here is that the picture that I should be looking at is something like this. Is that there's this force picture, and we really don't want to use the force picture because energy is easy to deal with. And then there's the energy picture, but the force will help us in sort of like understanding what is going on. So here's what we find. We have a nuclei. And inside this nuclei are what? There are 2 protons, 2 neutrons. And there's little electrical force here. Why? Because there's only 2 protons. So it turns out that the electrical force is not so big in this case. Why? There's few. So here's the electrical force. However, the strong force is a whole different ballgame because the strong force binds everything together. So in this case, what we're seeing here is that the strong force binds proton to proton, neutron to neutron, and proton to neutron. So you're seeing lots of binding here because there's just so many of these guys in here. So when you look at the strong force in this situation, you're finding that the strong force is just much, much bigger than the electrical force. So what you see here is that now if I look at the energy picture, what do we see? Well, the binding energy is just so much larger. Versus the electrical repulsion energy. It's just tiny in comparison. Just tiny. And just one more time, right? This here is the attractive binding energy. This is the repulsive electrical energy. And so if we look at this picture here, so again, this just tells us that the binding energy is just so much stronger than the electrical one. That's really what we're saying right there. But one thing that I really want you to keep in the back of your mind is this. Okay, and I'm going to say that this is an important point. What is the binding energy doing here? So the strong or the nuclear binding energy is containing all of this electrical energy. So there's a lot of electrical energy in the nucleus, but because the binding energy, the nuclear binding energy is so much stronger, it's keeping it in check. It's containing it. It's almost like you have, I don't know, a balloon. A balloon has pressure inside. And as you pump up the balloon has to work harder. And that's what that nuclear binding energy is really doing. So let's go to the next one. So here I picked a different one. We picked silver last time. This time we want to pick something close to that, which will be copper. So when I look at copper, this is what I would call a midweight nuclei. So this is a midweight nuclei. And so when you see this guy, what does it really look like? Again, look at copper. It has 29 protons. Look at over here. Look at our picture that we talked about. See how it's 29 protons? So you could see it's in that midweight region right there. So it's exactly what we would expect it to be. So then if I look at copper, what are the details of copper? So if I look at copper, we could see here is that this is 64, 29. And then this tells me that it has 35 neutrons. And then this guy has 29 protons. Oh man, I forgot to do one thing on this previous example. Man, I can't believe I missed that. So what I'm going to do here is that I'm going to bring this here, and I need the space. I have to keep calculating the neutron-proton ratio. And so when I look at this tells me here that the neutron-proton ratio in this case is 1. That's the whole point of this thing here. Now let's calculate this thing for this guy here. So when I look at this neutron-proton ratio is going to be what? 35 over 29, and I get 1.21. Right? This gives me 1.21. What does this mean? There are 21% more neutrons than protons. So before we start to look at the force picture and everything like that, I think what's going to be important is that we make some remarks. Okay. So when I compare copper, which has 29 protons, and I compare helium, which has 2, we should have, let's make some observations. So the first thing that I would say is that comparing helium to copper has many more protons. So this immediately tells us that it has a much stronger repulsive energy, right? It has way more. So in order to contain this much stronger repulsive energy, so in order to contain this larger repulsive energy, more neutrons are required to glue the nucleus together. So if you had, for example, 29 neutrons and 29 protons, the electrical force is stronger. So for example, if we had 29 neutrons and 29 protons, then what you find here is that the electrical repulsion is greater than the binding energy. And so what this tells us here is that the nuclei would not exist. You need more protons. So what you find here is that by adding more protons, it's now stable. Okay, but since there are 35 neutrons and 29 protons, then this is sufficient to hold the nucleus together. And that's what the role of the neutron is. So when I start to look at the picture here, what do I find here? Well, if I look at my force picture, what I see here is that there's a growing strength in the nucleus that's repulsive. So if this is my nucleus now, I'm not going to count how many protons in detail here, but what you're seeing here is that there should be a lot more blue than red. And so what you're seeing here is that now this force is growing and it's pushing, trying to blow the nucleus apart. But because we add more neutrons, we're seeing that the nuclear force is now stronger also. Right? So in this case, we say then that the strong force is having to work harder to keep the nucleus together. So when I look at the energy picture, what do I see here? Well, in the energy picture, because I have more neutrons and protons, I have a larger binding energy. So the binding energy gets even bigger here. It has to in order to survive. But what you're finding here is that the binding energy compared to the repulsive energy is also growing. Now, why is this growing here? Well, oops. What we're seeing here is that we're seeing this, is that right here, we have what? We have more neutrons. If I have more neutrons, I now have more, I have a higher binding energy. Whereas here I have more protons, so therefore I have a higher repulsive energy. And so what we're seeing here is that in summary, we could then say that the strong binding energy is having to work harder to stop the nucleus from blowing apart. Because that's the role of the protons. They want to continue to do what? They want to blow the nucleus apart here.